relationships that we're looking at are about size. Some is the size of a natural atom. Some are the size of the ion that we might create by gaining or losing electrons. The other three trends have to do with electrons, right? One of three things. We're either trying to hang on to one, which is called ionization energy. We're trying to attract the electron of another atom, which is called electronegativity. Or we're having a release of energy when we get that other electron to enter our electron cloud, which would be called electron affinity. So quick recap of what those are. Atomic radii, right, or the radius, if we're talking singular, technically is half the distance between the nuclei of two identical atoms. So if I'm going to measure the size of an atom, right, you could think of it as like a circle, and we're trying to measure from the nucleus to the edge of the electron cloud. But that's a difficult task because the edge of the electron cloud is not really easy to detect because the electrons are moving around all the time. So what they decided to do, and why they pluralize it, is they take two identical atoms and put them right next to each other. And then they measure the total distance from one to the other. And they know half of that distance, when we split it down the middle, is going to be where the electron clouds run into each other. So that's how they define the size of the atom. All right, so when I say atomic radius, it means one atom, and radii is just referring to how big the atom is. So somewhere where you're jotting down little things to remember, you wanted to say that atomic radii is the size of the atom. Visually, if you look at the periodic table, as you go across the table, you can see the atoms get smaller. As you go down the table, atoms get larger. So from lithium to sodium to potassium, the atom is getting larger. As you go lithium to beryllium to boron to nitrogen to oxygen to fluorine, the atom is getting smaller. It is shrinking. Today, we're going to talk about why that is. All right, so there are three ideas that we will use to explain why any of these particular trends occur. And those three ideas are what you see down here. First is called the effective nuclear charge. Right? And the effective nuclear charge is simply the charge felt by the nucleus on those electrons on the outside. Generally, the nuclear charge is how many protons the nucleus has. So if you think of an atom, the more nucleus it has, the more protons in its nucleus, the stronger of a pull the positive charge is putting out. However much the electron feels that pull, is called the effective nuclear charge. The second idea we'll use to explain some of these trends is called electron shielding. All right. Whenever we build an atom, we knew that there were rings that later developed into orbitals, right? But you had a ring, then another ring, then another ring, then another ring. Each time you add a ring, you're dumping a lot of electrons in between the outer electrons and the nucleus. Think of them as blockers, right? Those inner electrons, which are called core, they will block outer electrons from feeling the nucleus, and that has effects. The last thing that we'll explain or use to explain some things is called the octet rule. You're going to find out that there is a really big energy stabilization, which is why most atoms behave the way they do. Whenever atoms achieve 8 valence electrons, all right? And the reason being, when you get 8 valence electrons, you have a fill shell, right? You have an S2p6 configuration, which means all of your orbitals are filled. There's an exception to that, right? Helium and hydrogen, because they're in the first row, only have to fill a 1s2, and that fills their whole energy level. So they follow what they call a duet rule. So just think of it as an exception to the octet rule. So these three ideas will be able to explain all of the trends that you see listed. all right, here on the table. All right, so if I go through those one by one to give you a feel for what they are, right, the nuclear charge. Right, the nuclear charge is how much an electron on the outside, like this guy, feels the nucleus. All right, so the nucleus is positive, the outer electrons are negative. Opposites attract. They call it electrostatic attraction or Coulombic attraction, but just remember, opposites attract. Right, so those nucleus protons are sending out a pull. Think of it like a magnet, even though it's a different pull. All right, it's pulling on these electrons. So the more protons in the nucleus, the more the electron will feel that pull in an energy level. That's called nuclear charge. Right? And the abbreviation for protons is Z. And we're talking about the effectiveness of the proton. So they tend to call this ZEF a lot. Z-E-F-F, Z effective. All right, so if you hear me say that, I'm just talking about the pull from the nucleus. All right, so I have this link down here, right, which you guys could always access as well. And that will take you to a site where you can build an atom. And I'm going to show you how that all ties together. All right, but this is what effective nuclear charge is. All right, the second one is electron shielding. All right, the electrons that are most prevalent in participating in reactivity, most prevalent in making bonds and things like that, are those valence electrons, right? And we've talked about why those are important. They have their own structure. Remember, we did our dot structure, which was the valence electrons. All right, those electrons are particularly important. So the ones on the outside, outer electrons, are called valence. There's electrons underneath of them, though, that are closer to the nucleus. These two guys and these 8 in the first ring and the second ring, they call those core electrons, right, or inner electrons. But what happens is, what keeps this electron where it is the nucleus, that positive pull from the middle. And if there are blockers in between, that means they can block this electron from feeling the nucleus. That's electron shielding. Electrons that are in the inner subshells block out the ones on the outside. All right, so if we want to explain trends in radii, why atoms get bigger or atoms get smaller in a direction, right, it depends on which direction we're going when we want to explain that. So I first remind you here of what is the trend. Radius decreases across. Atoms get smaller going across, and they get bigger going down. So what I'm focusing on right now is, why do they get smaller as we go across the periodic table? All right, and the best way to do that is to build an atom for you. All right, so if I take you over here, all right, what I have here is the ability to build an atom. So I can pull out protons as I need. And remember, the protons is what makes you who you are. And then these are electrons. Right? It helps if we start from scratch so you can see the whole process. Oh, wait, reset. There we go. Perfect. Okay, so let's say I want to build an atom. I drop a proton in the nucleus. I now am hydrogen because only one element has one proton. It's hydrogen. I drop another one in. I've become helium. I've dropped another one in. I'm lithium. I drop another one in. I'm beryllium. But I'm going to stop at lithium. All right, so lithium's whole number in its box is 3. It has 3 protons, but that also means it has 3 electrons. So we put 1 electron there, and notice if I drag it here, it takes it where it should go. Those first 2 electrons fill the 1s2 orbital. I take a third one. It drops it now into the second level, because after the 1s2 fills, we get the 2s1, right? Think about our electron configurations. Okay, so here's the atom. Now, there's neutrons in here, but the neutrons really aren't affecting our conversation. So I'm not even going to put them in there. Okay. All right, so you get this electron right here. I'm focusing on this guy. All right, right now, all right, let's keep it simple. All right, Izzy, how many rings of electrons are there? How many of those rings have electrons in them?
3.
So a dashed line is a ring. I'm sorry, I should have said that. So not how many electrons, how many rings have electrons on them?
Oh, 2.
There you go. All right, so there are 2. Right, so we have electrons in the 2 rings. All right, so if I'm going to work my way across the table, all right, what happens is I go to beryllium next, which means I add a proton. And yes, I add an electron as well. All right, but now watch. All right, same question, all right, except to Jackson. Jackson, for beryllium, how many rings have electrons on them?
3. No, 2.
Still just 2, right? It now just put a second electron in that 2s orbital. All right, so we keep going. We go to boron, right? We're working our way across. Right? That means I add another electron, right? It would go there. All right, Nick, all right? How many rings have electrons on them now?
2.
Good. Still just 2 rings of electrons, right? I now just have 2s2, 2p1, right? And we keep going. I drop another one in. I'm now carbon, another electron. It goes there. All right, Hannah, how many rings have electrons in them?
2.
Still just 2. So as I go across the table, I am not increasing the number of rings that the atom has, right? I go from 2s1 to 2s2 to 2s2 to 2p1, 2p2, 2p3, and so on and so forth, till finally we get all the way down to neon at the end of the row. And I've now emptied the protons and electrons out, right? But I'll ask Jimmy, hey, Jimmy, how many rings have electrons on them?
2.
Still just 2. All right, so we didn't increase the number of rings. All right, so the atom's not getting bigger because we're adding energy levels. All right, so the question becomes then, well, why is it getting smaller? Well, don't forget, every time I put a blue electron onto the ring, I was dragging a proton into the nucleus. So look at the nucleus of lithium all the way at the other side, right there, compared to neon, who we finished with. All right, so if we look at that, Morgan Pusula, whose nucleus is bigger?
Like between what?
Between the lithium, where I had just 3 red protons, and the neon, where I now have 10.
The neon.
The neon. So the neon has way more protons in its nucleus, pooling on the same 2 rings as the other elements in the row. And because it's got a stronger nucleus, it can pull the rings in tighter. So it pulls them closer to the nucleus, and therefore the atom shrinks. So as you go across, you're not adding any new rings, and the nucleus is getting stronger, the atom gets smaller. That effect they call nuclear charge, effective nuclear charge. So why does the atom get smaller as you go across? You would say it's got either greater proton pool or it's got a greater effective nuclear charge. All right, so as we go across any row, the number of rings stays constant, but the protons gets bigger, so the atoms get pulled tighter. The outer ring gets pulled closer. All right, so that's what's happening as you go across. All right, let's talk about what happens as you go down the group, right? So on the notes here, I say as the nuclear charge increases across the row, it's able to pull the electrons of that outermost ring in more tightly, therefore they shrink. That's what this is saying, and then think back to when we were building the atom. All right, well, what about as we go down? All right, as we go down the columns, atoms are getting bigger, right? Sulfur is smaller than selenium. Let me show you why that is in the other one. All right, so we reset. I want to work my way down a column. So I'm going to start at hydrogen. It has one proton. It has one electron. All right. Start simple. All right, Antonio, how many rings have electrons in them?
1.
Just one. All right. Now, if I go down to lithium, lithium on the periodic table has 3 protons and 3 electrons. All right, so that's the difference between hydrogen and lithium. All right, 1 proton in the nucleus versus 3. 1 electron on the outside versus 3. But if I ask Audrey the question, Audrey, how many rings have electrons on them now?
2.
2, right? Because after I added that 3rd electron, it couldn't go in that first ring anymore, right? So when we go down the column, each time we move down a row, you are adding an energy level. The atoms have gotten so many electrons that the previous ring can't hold it, so you go again. And then you move down a row and you go again. And the way you know this is if we work down the first column on the table, I showed you hydrogen, and you knew it had 1 electron. It's in a 1s1. Then we went to lithium. Its last electron is in a 2s1, right? Using our trick. Rows down, s block, 1 over. If we go to sodium, it's a 3s1. If we go to potassium, it's a 4s1. If we go to rubidium, it's a 5s1, and so on. Cesium, it's a 6s1. So each time I move down a row on the periodic table, I have to add an energy ring. There was 1 ring. Now there's 2 rings. Now there's 3 rings. Now there's 4 rings. And I'm running out of space. But you get the idea. Why does the atom get bigger as we go down? Because you're adding energy levels. Think of it like you're adding floors to a house. As you add floors to the house, it naturally has to get larger. All right, so that's what's going on with both of your radii trends. As you go down the columns of the table, you are adding energy levels. And adding levels increases the blockers in those subshells. Therefore, atoms get bigger. All right, so there's the first 2 trends because radii work the same way. The next 3 trends all pair together as well, because if you look back at your chart here, notice that the ones that say radii decrease across, they get smaller and they increase down. And the ones that don't say radii do the opposite. They increase across, they get bigger going across, and they get smaller as they go down. Let's talk about why that is. All right, so we did the 2 that had to do with size. Now we're talking about electrons. All right, so friendly reminder, ionization energy is how difficult it is to remove an electron. I'm claiming it increases across. It gets harder to take an electron as you go across. All right, so imagine I'm trying to take the outermost electron, a valence electron. Right? It gets more difficult as I go across to take an electron for the same exact reason the atom gets smaller. All right, so ready? Watch this. We're looking at lithium. I'm trying to steal this electron from the lithium, his outermost one. All right, if we go across the table, all the way down to the neon. And I now have got my 10 protons. And my 10 electrons. All right. All right. Look at what happens with the atom. All right. I'm still trying to take this electron. All right. So I'm going to ask a couple questions. All right. Osho, that electron I'm trying to take, is it any further away from the nucleus than it was originally?
No.
No, it's still in the second ring, right? So they're all still in the same ring. But the big difference between neon and lithium, who is back at having 1, is that neon has 10 protons in its nucleus and lithium only has 3. So these electrons out here are feeling way more pull from the nucleus. And before I said that pull made the atom get a little smaller. It shrunk them down. Well, the same thing that's pulling them in toward the nucleus makes it harder for me to pull them out, right? So if you think about it, oh, the atom gets smaller. Now it's harder to take an electron because it's closer to the nucleus. So ionization energy measures how hard it is to pull an electron off. And they call it that because when I pull an electron off, I make an ion. Notice, look what happens. Neutral atom right here. When I pull an electron out, positive ion. That's why they call that effect ionization, the process of becoming an ion. All right, to do it, I have to rip an electron away. Right? But because there's so many more protons in the nucleus, it gets much more difficult as I go across to rip that electron away. All right, so that's why ionization energy increases as I go across. All right, why
Mr.
does
Reed,
yes, ma'am?
can you make a negative ion too?
I can. If I wanted to make a negative ion, all right, let's say we started with fluorine, which had 9 protons and 9 electrons. If I put another electron into the cloud, I make a negative ion because now I have 10 negative electrons and only 9 positive protons. All right, and they give those names like we talked about. The negative ion's called an anion, and the positive ion's called a cation. All right, and we're going to talk about that because what I just showed you here, when I made that positive ion, was ionization energy. When I'm adding an electron in, that's my electron affinity, which is our last one we'd have to talk about after this one. So great question. Okay, so moral of the story, as you go across, the nuclear charge, the nucleus gets stronger, so it's harder to take an electron. So the ionization energy goes up for the same reason the size goes down, all right, because the nucleus is stronger. As you go down a column, it gets easier to take an electron. Watch why. Right? We're looking at hydrogen again, which looked like this. All right. Right now, all right, Justin, what ring is the electron living in?
Here's my problem.
So the first ring, the ground state.
Exactly. It's in the first ring. Now, if I make it become lithium, I toss 2 more protons in, and you're going to say, well, wait, the nucleus is getting stronger, but I also have to toss in 2 more electrons. All right, now, all right, you have to look at this and cross how many rings have electrons in it.
3.
Careful, just
Right.
dash lines, 2. Right, 3 electrons, but only.
Oh, okay. I see. Sorry. I'm still kind of asleep, so I'm like seeing doubles.
We'll get you going. We'll get you going. All right, so the moral of this story is when I was hydrogen, I was taking an electron out of the first ring. All right, which is tough because it's close to the nucleus. But then when I move down the column to lithium, Colton Clark, where am I trying to take an electron from now?
The second ring.
The second ring. So the reason is I go down that it's easier to take an electron is it's further away from the nucleus. Yes, the nucleus is stronger, but the electron I'm taking is a lot further from that nucleus. So now I'm trying to take one from the second ring. And if I go back to here and show you, right, when I get to sodium, I'm pulling electron from the third ring, so it's even easier. Potassium, I'm taking one from that fourth ring away. Rubidium, I'm taking it from the fifth ring away. All right, so as you go down a column, it gets easier and easier to take an electron, so the ionization energy goes down. All right, and that's what this is saying right here. As the nuclear charge increases across, it's harder to take an electron. All right, And as we go down a group, you're adding energy levels. There's more rings. There's more shielding of those electrons underneath, blocking that outer one. So he's easier to take away. All right, questions on the taking an electron away one. That's one of the like trickier things we'll do. All right, last trend for the day. Right, electronegativity and electron affinity. They basically work the same exact way. All right, so these two trends measure something very similar. Electronegativity is the ability of an atom to attract another atom's electrons. Right, electron affinity is the energy that you release when you finally convince them to join your electron cloud. All right, so the trend for both of these is that it increases across until the noble gases, and it decreases going down. All right, so I'm going to go back to where we were. All right, as we go across, you're currently looking at lithium. What controls its attractiveness is how many protons it has. So we're talking about, for electronegativity, not lithium attracting its own electrons. We're talking about it attracting an electron from another atom, say over here. All right, so right now, in the nucleus, Dylan Cade, how many protons are there to attract? Like how many red guys are in the nucleus? Oh, Dylan, I think your microphone's off, buddy.
3.
All right, 3, very good. So there's 3 protons in the nucleus. Pooling. All right. As we go across and we work our way to neon, the nucleus all of a sudden looks like this, and he's still trying to attract an electron out here. All right. And Jennifer, how many protons are in that nucleus now? Jen, I think your mic's off too, hon. Okay, we will come back. All right, birthday boy, Tyler, how many protons are in my nucleus?
Uh, 10.
10. So Tyler, who's going to have a stronger nucleus, lithium with its 3 or neon with its 10?
Neon.
Neon. So because it's got so many more protons, it can pull and send out like a field. Think of it like a magnetic field, even though it's not, right? It's got a much more attractive ability because it's got 10 protons in the nucleus. So what happens is it can attract this electron better. And when it gets here, it releases more energy when it finally enters into the cloud. So electronegativity is attracting this guy, and electron affinity is the energy released when he enters the cloud. Okay, so they go hand in hand. So as you go across the table, the attractiveness goes up, and the energy release when it enters goes up as well because the nuclear charge increases across. As you go down, those things decrease. All right, as I go down the table, I don't attract as well. Right, and the reason why isn't because it doesn't have enough protons. Right, if you look going down a group, like bromine here has 35 protons. That's plenty to pull. And if I drop to iodine, it has 53 protons. So it's got way more protons, but don't forget, every time you drop down, you add a ring of blockers. So there are all these guys in here that are blocking that positive charge from getting out. So an electron way out here can't feel the nucleus nearly as well because there's so many rings, energy levels, and so much shielding that's chewing up that positive charge. All right, so the reason why things are less attractive down the table is because of electron shielding. All right, now, the last thing before I get you guys a breather here, is that both of these trends have a noble gas exception. They increase across until the noble gases, and then they shut down. Right? The affinity increases across until the noble gases, then it shuts down. And the reason why it shuts down is because when you get the filled outer ring, they don't want to attract anymore. So if you ever want to explain a noble gas exception, you want to use what we call the octet rule. When atoms achieve 8 valence electrons, 8 dots on the outer ring, there's a big energy release that makes them not want to attract more because it destabilizes them. So why don't they attract? Because they filled the octet rule, is what you would say. So this is the why these things occur. And a lot of times, in my experience, if you guys understand why things happen, you don't really have trouble remembering the what, right? Oh, okay, what happens? Does an atom get more attractive as you go across? You just have to think about it. Oh, same rings, more protons. Yeah, it gets more attractive. The nucleus is stronger, right? And that can help you guys not memorize nearly as much. So questions from you guys related to your periodic trend. All right, so here's what I want to do. I'm going to stop recording.